So I will press on. So you can see the title. This is a Rolls-Royce view. It's not an ICC-AIA view. The ICC-AIA represents aircraft and engine manufacturers, and you'll know who they are, but Rolls-Royce is only one of them, and this is a fairly unique stance that Rolls-Royce has taken. So I'll take you through. Hang on. It's coming. Good. This is the running order. Oh, it's on my screen. It'll get to yours, I hope. Yeah. A bit of a talk about what volcanic ash is in relation to aircraft engines. And there is a very strong analogy with desert dust, or mineral dust, as it's more scientifically called. And I'll talk a bit about the geology associated with volcanic ash and mineral dust, then cover a bit of the aviation world policy on volcanic ash in terms of regulations and guidance. And actually the bulk of the presentation is the final point, which is pragmatic engineering and how it might be useful to operators. So moving on, when it appears, you'll see a picture of a cutaway engine. In fact, yeah, there you go. This is a Trent 1000, one of the engines that's used to power Boeing 787. But you can see it's an artist's impression. It's been cut away, and the coloured bits, the blue, the sort of yellow, red, and then back to green, that's the engine core. Now that's the bit of the engine that is most vulnerable to volcanic ash and actually mineral dust as well. There are a number of damage mechanisms that both these phenomena can cause engines, but the two critical ones in terms of engine operability. So the things that will stop your engine working in the short term will be, as you can see there, excessive erosion of rotor parts in the compression system, or both, deposition of a partially molten or fully molten deposit on the inlet aerofoils to the high pressure turbine, the nozzle guide vanes. So if you don't need to completely block that passage, but if you reduce the flow area by between 10 and 20%, most modern engines will they will stop, because you're reducing the flow of air through the whole core of the engine, and the compression system will struggle if it's really got to work hard to push the air coming in at the front essentially against a pressure gradient that it doesn't want to it naturally will resist, and you'll end up with the hot gases coming forwards, not backwards, and it's a surge. And when it appears, there's the only photograph I could find on the internet of an engine surging. Now, I stress in the bullet points below that there are other, and I've already said it, there are other damage mechanisms associated with these atmospheric phenomena, contamination of avionics bays such that the electronic components can get insulated by deposits, they start to overheat and can fail. You can get cooling systems partially blocked up, and they start to reduce the amount of cooling to the critical parts of the engine, and eventually they will overheat and fail. But all these mechanisms, which are common between volcanic ash and mineral dust or desert dust, take a very long time to manifest themselves. In even anything other than low, moderate to high, the damage mechanism which will get you first, will stop the engine running, will be one of these two at the top, the erosion in compressors or the deposition of partially molten material in the turbines. And actually most modern engines now are running sufficiently hot that the compressors will last longer than the turbine. So it's almost guaranteed that it will be the turbine that stops you. And it's this loss of high pressure compressor operability. Now, so this brings you to the point, well, I've talked already about volcanic ash and desert dust. Many people think, well, they're completely different. They represent completely different threats to aviation. One clearly has a safety implication. The other is, if you're aware of it, and some people in the room will be, has a durability of the engine, so a cost of ownership implication, which would be mineral dust. But there are similarities. They are both essentially made of aluminosilicate particulates, although desert dust, particularly the troubling stuff, has got a lot of carbonates and sulfates in it, which make it particularly interesting. But they are similar in their nature that way. But the key differences are, because volcanic ash has come from a molten rock, the magma, and which is cooled very rapidly and explosively, those particles will be made of an amorphous glass. And amorphous glass behaves differently when heated than a crystalline mineral that you get in deserts. So that's a big difference. So that affects the temperature at which they go soft and start sticking in turbines. The other big difference is that the volcanic material is fresh out of an explosive eruption, so it tends to be very angular and sharp, while much of mineral dust is weathered and rounded, so it tends to be less erosive. But that's only true the first time it's hit in the engine. By the time it's been milled up by the compression system, which happens, they become quite angular as well. So this is the basis that people had assumed was the big difference between volcanic ash and mineral dust. But actually, we are already beginning to realize in recent decades that many mineral dusts around the world, particularly in places like the Persian Gulf, parts of North Africa, and even East Asia and North India, are sufficiently rich in volatile components that they will start to melt at similar temperatures to volcanic ash. So my contention is, in terms of the melting and erosion behavior, if I had a choice, I'd rather fly mineral dust, but there's not a lot of difference in terms of that. So what is the big difference? So the next slide coming up, geographically, this is a bit of a general knowledge, not if you didn't know it. So they do occur differently on the planet at different locations, and it tend to occur at different altitudes. I won't dwell too much on this slide, but what I will pick out is there's some circles coming up. They've appeared, and I've already said this, but we're beginning to realize, and the evidence is clear, that modern engines, when operated in these regions of the world, the mineral dust is starting to behave like volcanic ash did 20 years ago. It will become molten and stick on the turbine bits. So why are engines in mineral dust not doing what BA9 did in 1982 or the KLM 867 did in 89 from Mount Redoubt? Now, I think this is the key difference. This chart that I produced some years ago, to try and illustrate it, it's along the x-axis is the concentration in milligrams per cubic meter, because that's a useful scale to use. It's a log scale, so in tens, and the vertical axes are, whether you work in feet or meters, the altitude, and you'll notice there's a sort of log bit near the ground, and then it goes linear. There's a reason for that, and you'll see that in a minute. So the key thing with volcanic ash, it can occur anywhere in this chart. The bottom left of it can be there because it's become resuspended from the ground. At very high altitudes, cruise altitudes, even into the stratosphere, you can get high concentrations of volcanic ash, typically associated with the eruption plume. Now, there's some photographs to illustrate that, some of the examples. It's coming, but the electrons are slow today, potentially like my brain. Here you go. There's another one coming. What'll appear in a minute is this sector of this chart where you get naturally occurring mineral dust. So this is mineral dust that is put in the air by wind. And it comes in, background concentrations of places like Doha or Delhi at the wrong time of the year. And even on a severe, when you get a dust storm, you'll get higher concentrations. But the highest concentration you'll get from a dust storm from wind is about 30 to 40 milligrams per cubic meter. Note that a volcano can put thousands of milligrams per cubic meter into the air because it's an explosive event. Some photographs coming up. You can get mineral dust up to cruise altitudes, but you tend to need a convection system to do this, and people will avoid convection systems for other reasons other than the fact there might be dust in there. So really, at cruise altitudes, mineral dust is not a problem. It's only really a problem during taxi, takeoff, climb, or descent and holding patterns, and it's naturally limited. Now, the pictures are coming up. There is one class of operation where you can get volcanic ash level or volcanic eruption level concentrations of mineral dust, and that's when you've got a helicopter or a tilt rotor and you're operating near the ground on dry, dusty surfaces, and the vectored thrust will throw out very high concentrations of mineral dust. This clearly won't happen in civil aviation because we just don't operate like that, but it is a problem for defense and military operators. I'm now going to take this chart and plot on some examples of actual aircraft incidents. And I use a convention of ellipses to show uncertainty in parameters. So the horizontal dimension of the ellipse indicates the uncertainty in the concentration. The vertical is the uncertainty in the altitude. There's a chart coming up later where I extend this to cover how long you're in ash or mineral dust, as well as the concentration. So red for safety implication, yellow for there was an impact, but it was purely economic. There was no safety implication. So I've picked, as you can see, 6 points here, and fair enough, you could criticize me for saying, I've cherry-picked these. Well, I have, but they're not unrepresentative of what will happen. I have been unable to find any red incidents to the left of this chart. There are some yellow, even green, either no impact at all to the right. But the only part of this chart where you'll get a safety implication are where those three red ellipses are. The solid colouring is for volcanic ash. The checked is for mineral dust. And you can see at the bottom there, the Oahu 2015, for those that are familiar with it, was a US Marine Corps V-22 Osprey, and it's the only one that involved fatalities. There's two of the US Marines on that aircraft when the engine surged. It was only 50 feet off the ground. Lost thrust hit the deck very hard, and tragically, two of the occupants were killed, but I think 22 walked away. Now, what I would suggest is, irrespective of whether it's volcanic ash or mineral dust, there is a region of this chart to the right of which you don't want to be because it has safety implications. Fortunately for civil aviation at the moment, for naturally occurring mineral dust, all the occurrences are to the left. But I have had conversations with regulators in recent years. The rate at which civil aviation is getting airworthiness directives to do with operations in naturally occurring desert dust, they're beginning to get concerned that modern engines are sufficiently vulnerable that they might start thinking about regulations to cover mineral dust. Right. Quick slide on the key points that have occurred really since the AIA events of 2010. There was the International Volcanic Ash Task Force that ran for 2 years from 2010 to 2012. The two key outputs, there were many outputs, but the two key ones I focus on are the general agreement, although I think it was a bit of a fudge, but we can have a lot of discussion about this, the principle that rather than avoiding a concentration of ash, we would encourage people, and it is only a recommendation, we would recommend that people avoid visible or discernible ash. It's an interesting discussion what actually those two terms mean. There isn't time today to go into it, but I'm happy to go into it later. What I wanted to focus on was the second point on this bullet point, which is it was agreed it's the responsibility and decision of operators when and where they fly in relation to contaminated airspace with volcanic ash. But it's agreed that the whole industry needs to support you in allowing you to make a good decision and keeping everybody safe. And it's done under safety management systems and safety risk assessments. Now, I personally believe one of the reasons that the ICCAIA members, of which I'm one, resisted going anywhere near a numeric value for ash concentration that you might think about in terms of operations was because there was a fear that it would lead to a certification requirement. Well, EASA, they were aware of that fear, but it didn't bother them because they've introduced one. They introduced one in 2013, 2015 for the engines, 2013 for the airframe, but they're essentially the same regulation. But it's a clever regulation for me because it says we're not going to tell you you have to demonstrate your equipment can cope with a particular level, but you can declare a level that you're comfortable with, but you've got to support it with evidence. So it is quite possible for a manufacturer, airframe or engine to say any ash, single grain of ash is problematic. So that's our susceptibility. It's not credible to me, but they can do that. And finally, the reason we're here today, 2018, there was an agreement through this forum or the IAVW that we would move from the black and white VAA, VAG, possibly ash, no ash, to the quantitative or concentration-based products or data, so QVA. Now, in relation to the certification rules that EASA introduced in 2015, because we consulted with our customers, the airlines, many are in the room, certainly in Europe, there was a feeling that because the concentration of 2 milligrams per cubic meter and 4 milligrams per cubic meter had been talked about in 2010, they wanted a susceptibility statement based around those values. So I was effectively asked to demonstrate at what level our engines can operate. One of the things I did, I realized I needed to do would be to build a mathematical representation of the effect volcanic ash has on engines, particularly the critical HP compressor surge. So the erosion in the compressors and the deposition of the turbine. This is the representation of it. Many people get scared by this kind of maths. It's actually pretty simple maths. It's a very simple engineering experiment. But the pictures on the left illustrate the key effects, and the bottom left picture illustrates when it comes to deposition, two very important effects. So there's one where the ash deposits and builds up on the aerofoil, but simultaneously, and there is clear evidence of this, and anyone who's not sure whether it's legitimate, I can furnish them with all sorts of evidence that proves the ash will spontaneously fall off. If the engine is running at a slow rate, it will fall off. In high concentrations, it falls off at such a slow rate that it's negligible. It's swamped by the amount of ash that's arriving and building up. But at moderate concentrations, you can end up with a balance between the rate at which it's arriving is matched by the rate at which it's spontaneously falling off. So a mathematical representation of that is in this model here. As with most science, but certainly all engineering models, you depend on empirical coefficients or parameters that have to be matched back to experimental data. And there are 5 in this model, 4 of them to do with engine, the deposition of the nozzle guide vane. I won't go into how we've verified those, but the information is available. The key thing with these kind of models is you can run them to all sorts of conditions: aircraft flight speeds, engine powers, type of volcanic ash, condition of the engine. And you can find the critical flight phase where you're going to get the most rapid loss in engine operability. And that's what we did. We needed to verify it against some experimental evidence, and there is some around, and I'll take you through it in a bit more detail. But to do that, there wasn't quantitative data, but there's qualitative data on the impact the ash exposure has on the engine. So I came up with these 4 categories. Green is negligible impact. We know the engines were exposed to ash, but there's no detectable impact. Yellow is there is some impact, but it's a minor impact on either increased fuel burn or slightly reduced maintenance schedule. You might have to remove the engine for major overhaul a few 10, 100 flights earlier. But you can see it's still a usable asset. You can still use that engine. And then you get into the orange. I called it exigent. So at this point, the exposure has been sufficiently severe that at the very least, you have to stop the engine, let it cool down, get a borescope, go inspect. And in the worst case, you'll have to remove the engine for overhaul. But you are safe. You got back to base safely. The red is there's clearly been a safety implication. The photographs back that up. What we found, and the evidence is clear on this, as well as good knowledge of the science going on, for a given engine type, for an engine condition, a given ash type, the thing that differentiates between whether you've got a green event or a red event is the concentration of ash you're in, but also how long you're in it. It's not just the concentration. It's a dose-based effect. You can be in a very high concentration for a couple of seconds. It's not going to kill your engine. You can be in a moderate concentration for hours, and you can end up with a problem. I built up a database. It's not a very big one, but it's very useful. And there's only 25 points on it, but it's sufficiently big that we can do some sort of data analysis on it. I looked around for all the volcanic ash events where there was useful data that I could understand the impact, the likely concentration that they were exposed to, and the likely time they were in it. And you can see that in the extract from the database. It's you can see it's a good quarter of the database. Notice that the concentration and duration of exposure column, I've got a min and a max. That's not the minimum concentration they were in or the maximum. That is the range. These are average concentrations. So for the Galungan 82, which is the BA9 event, depending on which evidence you look at and which authority you talk to, potentially it was at 2,000 milligrams per cubic meter. I think it was nearer 200, but it could have been as low as 100. So there's an uncertainty there. And you get similar levels of uncertainty in the duration. Now, many of you will have seen me build this chart up because of time and because a lot of people have seen it, but there are videos on the internet that show you this. I put all that data onto a single chart. So this is a new chart, which, again, concentration along the x-axis as a log scale in milligrams per cubic meter, but the y-axis is now time or duration that you're in the ash in hours. So 1 is 1 hour, 0.1 is 6 minutes. Because it's a log scale, the constant dose or the product of time and concentration, they end up as diagonals, and you can see the blue broken lines there. But you can see the spread of points from that database. And one of the lead statisticians in the UK, University College London, I worked with him on this, and he said, yeah, it is a significant number of points. It's not, there's enough points here that anything you infer from it is significant, it's statistically significant. Just about, but it is there. Now, what we did was take the mathematical model I showed you a couple of slides back, and plotted the behavior on here. So this is plotting the results of putting these concentrations in against these durations of exposures for different ash types, different types of engine, and you get this curve like that. And it's a reverse S because when it starts to go kind of vertical in the middle, that's where you've got the balance between deposition and shedding. You get this asymptote. And that effect was illustrated by the two orange points on the 10 milligram per cubic meter vertical line. They were the Viper 3 tests that were done with a C-17 engine, and I was involved with NASA and the US Air Force did that in 2015. And they'd reached a stability between they did 3 hours and then ran it for another 4. And the deterioration in the engine in the last 4 did not significantly get worse. They had balanced their rate of arrival with departure. And there's lots of other evidence like this. If you take, as I said there, it's coming up now, the worst ash type, the worst engine condition, the worst flight condition, you will end up with this bounding curve here. And I didn't mention it before, but at the top, where you're into the hundreds of hours of exposure, it's not deposition in the turbine that'll get you, it's the erosion in compressors or blocking up of the cooling systems. But you've got to be in the ash, those concentrations for so long for that to happen, it's effectively impossible. Now, this data allowed us to say, oh, quick, before I go on, I know Raymond will talk about this in a minute. There is an economic impact. Most of what I'm talking about here is safety, but there are economic impact implications, and that is important to airlines, clearly, and actually companies like Rolls-Royce, because in most cases we've got the financial liability for repairing them, unless we can come up with a contract that throws it back at you, but we haven't managed to do that yet. I know we're trying, but anyway. There is an economic impact that you need to understand, but as long as you keep it in the yellow, you're balancing, we're going to burn a bit more fuel for the next year and a half with these engines, and we might have to bring it in early for an overhaul, which probably Rolls-Royce is paying for anyway. So, but you need to understand the implication of that. But this is true of operating in the desert as well. There's similar implications. Anyway, go back to the safety implications. What we did to satisfy the requirements of EASA was declare this envelope. It's broken into 3 regions, but to the left of this sort of trapezium-shaped blue broken line, which I've colored in green, we can demonstrate there are no significant implications on flight safety from operating in that. And the exposure dose, the product of concentration and time, is cumulative. It's not one exposure. So if you the magic number is 14.4 grams seconds per cubic meter, which works out at 4 milligrams per cubic meter for an hour. You can do the conversions. So if you had a set of engines that did one flight 5 of those, and another second flight another 5, you've only got 4.4 left for your third flight. It is cumulative. So to the right of that, we're saying the operation means you venture into that region, you need to at least stop and do a thorough inspection of the engine. I personally believe if I had more evidence, if I could persuade Rolls-Royce to do an actual volcanic ash test, it's likely we could actually extend that envelope to the right and slightly higher. It is cautious, but I believe it gives lots and lots of operational flexibility. Just to recap, so there's the 3 regions. So below 0.2 milligrams per cubic meter, it's essentially unlimited dose. Treat it as background, as benign. Between 0.2 and 4, and the 4 is interesting because it was the number that EASA said, if you want to declare an engine susceptibility based on a concentration greater than 4 milligrams per cubic meter, you have to do a test. And I have failed to persuade Rolls-Royce to do a test. That's the limitation on that. Above 4, I don't say, in fact, I think I've got it here. It's not a brick wall. If you hit 4 milligrams, the engine's not going to suddenly fail. What we say is we can't specify what the exposure acceptable dose is. I think it will be less than the 14.4. It might be 12. I know the number because I can work it out, but I'm not allowed to tell you unless I can back it up with a test. But we're all good friends, or hopefully we will be. There's negotiations on that. Hopefully that wall will disappear in a minute. So, all right. So back to this envelope. What we've done, and it should be available for those people who operate Rolls-Royce engines that are Trent, RB211 and Pearl engines from Rolls-Royce Deutschland, you'll get information like this through the FCOM or the aircraft maintenance manuals. We do include this data information in the engine operating instructions, but that usually goes to the airframer, not to the airline. But in principle, there's no reason why airlines cannot get copies of the engine operating instructions. And there's a lot of information in there other than just those rather dry words, which are a representation of the graph on the right. I think the bullet points coming up illustrate that. We give guidance on if you reach this magic 14.4 grams seconds per cubic meter number, what you can do. And it isn't necessarily curtains the engines or a write-off. No, there's lots of things you can do. An obvious one, and we certainly do this when people fly in dust storms, don't go near a dust storm or an ash cloud for another week. Fly in clean air, do an inspection, and there's a fair chance a lot of the deposit will have removed because it does fall off of its own accord if it's on a high power. I did mention visible and discernible ash. We've produced data based on the evidence we've got of where these kind of effects are apparent from the flight deck, so we can offer guidance on that. How would you use this susceptibility? Now, this example goes back to the world of 2010, 2011, and actually probably still current now because I think Meteor France and the UK Met Office produced these products today if there was an eruption in Europe, concentration bands like that. So this fictitious eruption in a part of the world that doesn't actually exist, if you're flying from city A to B and you're presented with this ash cloud, what can you do? Well, one thing you can do is assume that in the blue or the cyan that everywhere it's 2 milligrams per cubic meter. That is very pessimistic. Almost certainly won't be the case. It'll be a lot less than that. And in the grey, it's always 4. But those numbers you can use to calculate your exposure dose. So these examples illustrate the how long you'd need to be in that ash, and it's a long time. You take flight plan example 1, 79 minutes. That's an awful long way. In 2 milligrams per cubic meter, you've only accumulated 9.48 grams seconds per cubic meter. So I think it gives lots of flexibility, and these are very, very conservative calculations. And I'll note here, it won't be the flight crew doing these, it'll be the flight operations people who will do it before they take off, and we would recommend they recalculate the likely exposure once the aircraft has landed. I'm nearly there, folks, by the way. The advent of QVA, and we'll talk more about this today, a bit more complex because the 4 milligrams per cubic meter is gone and it's now 5 milligrams per cubic meter, but there's ways of dealing with that. But I won't dwell on that slide. Just to illustrate that we do take safety very, very seriously, there was a scenario that dawned on us about a good year and a half ago that in principle, if you had a really old set of engines on your aircraft, and you flew for an hour in about 4 milligrams per cubic meter, and you started your descent within 15 minutes of leaving the ash cloud, and you did a go around, and the ash was made of volcanic glass, and there's a whole stack of these. In principle, you could end up with not quite or just about enough surge margin, which you'd be okay, but you don't want to be that close. So we worked out what the probability of that scenario would be. It turns out the most difficult factor in all this to put a number on is how likely is it that even if someone was trying to, that they can actually successfully fly for 1 hour in between 3.5 and 4 milligrams per cubic meter. Turns out it's very, very difficult. But because that was difficult, what we did, we worked out likelihoods of all the others, and you can see the numbers here, and it's pretty low. So the magic number, actually, it's not as small as 10 to the minus 9, because that's per incident, not per flight hour. The aviation industry works at, you're allowed one hazardous event, 1 in 10 to the 9 flight hours. So if you divide this by another 10, because flights are typically around 7 to 10 hours, you're an order of magnitude lower. But to get to that 10 to the minus 9, you only need the probability of that number 4 condition to be about 1 in 84. Talking to volcanologists, they think it's going to be an awful lot harder than that to achieve that, and we can furnish you that. What's interesting, though, is that this approach said to us, potentially this kind of stacking up of unlikelihoods or probabilities is the sort of thing that might be appropriate for operating with QVA when there's a probability of a certain ash concentration in the atmosphere. So just an example, my final point, I think I've done well here. I've left 5 minutes. That's good, just for me. rather than do this full study, because this is a specific flight scenario that you're unlikely to encounter, and my colleague from British Airways has indicated another interesting one, which Richard I have thought about and I can answer, that what happens if the flight crew switch one of the engines off on approach because they're worried what it will do. It does change these numbers a bit, but it doesn't shift them massively. But you could do it for those questions I've got there on the final bullets. What is the likelihood of being in ash for more than 1 hour with using QVA? And of that hour, what is the likelihood of it? If you said the target will stick to 2 milligrams per cubic meter, gives us 2 hours. That's a lot of flexibility. And distal ash clouds regularly have got ash below 2 milligrams per cubic meter. What's the likelihood that we've exceeded 4? There's a bit of work that needs to be done on this, and I'm really thinking about it. And I'm going to engage with people and help them construct a statistic or a probabilistic argument like this. Anyway, I've talked long enough. Thank you very much.